to bring genetic therapies to people with CF. Now, I'll preface my remarks by saying that, obviously, the approval and utilization of Trikafta has had a huge impact on people with CF, families, loved ones, and such. And it's really something that's been life-changing. And as happy as we are for people who've benefited from Trikafta, there are people who have not been able to take advantage of Trikafta. It's been described that there was a big party and I did not get the invite. Is sometimes how people describe themselves who have not been able to use Trikafta. So clearly, there's a need, and we need to keep working hard to develop CFTR-based therapies for everybody, and that's going to be the focus of my talk today. These are my disclosures. And so I want to just walk through what the CFTR modular timeline has been, just to give you a perspective on how long it takes to bring something from initial approval to having something that's available for the vast majority of people. And, the first thing that was approved was ivacaftor. First, people who were over the 6 years of age, and then incrementally it got to a younger and younger group, and now it's approved for infants at 4 months. But it took us about 8 years to get there after initial approval. And then if we look at lumacaftor, ivacaftor, which is Orkambi, again, you see that incrementally we have gotten into the younger age group. Then finally, Trikafta approved in 2019 for 12 and above. And then 2021 in the 6 to 11 group. And then we are anticipating, hopefully, that Trikafta will be approved for the 2 to 5 year olds sometime this spring. Orkambi's been approved for down to 1 to 2. And then eventually we're hoping that Trikafta will get down to the very, very young patients. But it just shows you how long it takes to get initial approval to get it down to a group that is, dealing with CF at a very young age. So just to get off for a perspective. Now, I alluded to this idea of patients who don't benefit from highly effective modulator therapy. And I thought I would take a minute to define, which people those are. Well, obviously, that includes people who, based on their genotype, and these are specific mutations that we don't feel are responsive to modulators. It's not like we wouldn't like to use modulators in those people, but their mutations, based on what we understand what happens, are not going to respond to a modulator. And there's a percentage of people who are started on highly effective modulators, but have side effects, adverse events that are intolerable, and they have to stop their modulators. Even if they stop and restart them, the side effects come back, and so they're unable to utilize these medications. So clearly, they would have a need. And there's another group of people on modulators that maybe don't have as much of a robust clinical effect as the majority of our people with CF from Trikafta, and then there clearly would be looking for additional CFTR targeted therapies. And finally, an argument can be made that every person with CF could benefit from additional CFTR rescue. At the end of the day, as well as Trikafta works, it is not a cure. We still haven't normalized the lung airway physiology with Trikafta as far as we understand. And so we need additional treatment for virtually every patient to really feel that we've got a cure for CF. So this is kind of defines a little bit of the group that needs it. But if you look at it a slightly different way about what are the backgrounds of people who are not benefiting from Trikafta, you can see that disproportionately our Black patients and Hispanic patients have a higher percentage of people based on their genotype who are not eligible. And this is registry data for patients 6 and above. So this seems to disproportionately impact the idea that Trikafta will not be an option for them of people who are Black and Hispanic. So clearly a disproportionate amount. So I use that as a background to understand, what the magnitude of the problem is and what we have to do. So what options do we actually have? Well, I'm going to take us back to our high school biology class and show you a diagram of what we're thinking about. So we know that CFTR is coded in the DNA of our cells. And we get one mutant gene from our mother and one mutant gene from our father. And this is, and once we get it, you have two mutations, and this makes abnormal mRNA. This mRNA is then made into a protein, and this is a mutant CFTR protein. And it's the protein that has the sort of the functional workhorse of the cell. This is what actually does the work of the cell. So think about the DNA and mRNA as sort of the software of a cell. The protein is sort of the hard drive, if you will. So what we've had so far is working on the protein, which is what Trikafta works on. But if you think about it, if you could actually replace the mutant RNA or the mutant gene with a normal mRNA, normal CFTR mRNA, or a normal gene, then that could be utilized to make normal protein, which could then rescue the CFTR dysfunction in a cell. So conceptually, that's what we're talking about when we talk about genetic therapy, either replacing the mRNA or the DNA. So I'm showing you this to highlight what the differences are. So I'm going to talk primarily today about programs that are in development that target either the mRNA, which is shown on the left, the circle on the left, it says RNA and mRNA delivery. And also talk about gene delivery, which is the DNA. And I highlight that as a path to a cure along with proteins, because that's where we're actually targeting the underlying cause of CF. And this contrasts to some of the other medications we've used historically, such as pulmozyme, inhaled antibiotics, hypertonic saline, which really are working to prevent some of the complications or treat some of the complications of CF, such as bronchiectasis, mucopurulent sputum, chronic infection. But with these other therapies, we're really targeting the underlying problem, which is obviously more attractive. So to talk a little bit about mRNA in detail, and one of the things that's important to remember that we've learned over the last few years is that what we want to rescue is CFTR in the airways. And it turns out that there's different types of cell in the airway. It's like a village. You have different cells. The two most important ones are probably secretory cells and ciliated cells. They have different functions within the airway. And it turns out that more CFTR is made and expressed in secretory cells. Now, underlying these cells is what we call basal cells. The basal cells are sort of the stem cells for the airway. That's a self-renewing population of cells. So theoretically, if you could get the mRNA into the basal cells, you might be able to have a longer effect. The problem is that they sit underneath this layer of ciliated and secretory cells, so it's hard to actually get at those cells. So that's just a little sidelight to help understand the heterogeneity in the airways. But the idea of mRNA is to get this mRNA into a cell where it can be used to make the normal CFTR protein. And one of the issues with mRNA treatment, it does not last that long in the cell. And so the protein will only be present for a limited amount of time. We don't know exactly how long that is, whether it's a week, a month. It's probably in that ballpark there. But it will need to be re-administered periodically to get sort of replenishment and more protein made. It doesn't necessarily require delivery to basal stem cells, which are sitting at the bottom of the mucosal layer. In contrast, gene therapy as opposed to giving mRNA, where we're actually delivering with gene therapy is the actual gene itself. So here the concept is that you deliver the gene that's codes for a normal CFTR, and that gene will be made into a normal mRNA, and that normal mRNA will be made into a normal protein. The advantage of gene therapy is that it tends to be a little bit longer lasting than mRNA therapy. So it doesn't perhaps need to be dosed as often. It probably does need to be redosed because we're not getting into the main DNA molecule. It sits sort of outside the DNA molecule, but maybe the delivery doesn't, or the redosing will not have to be as frequent. And again, this does not require delivery to the basal stem cells, which are the self-renewing cells of the airway. And a concept I'll just mention briefly is called gene editing. And this is a little further away in terms of coming to clinical testing. But the idea here is that you actually are able to deliver certain enzymes into the lung, into the airways. And these enzymes then, because they're so, they're engineered in a certain way, that they can actually repair the mutation that is in the endogenous DNA of a person. So here, if you could potentially get to the stem cells and change the gene, this is what we call actually change the endogenous DNA. You could actually have a cure if you could get into the right cell, which is a stem cell, enough cells that you could actually have a self-renewing cells that are making normal CFTR, mRNA, and normal protein. So this could be, in concept anyway, a one-time cure. Again, this is in development, but probably a little further away than DNA delivery and mRNA delivery. But this is something that's also being looked at. So one of the important aspects that we look at these drugs being developed is that these molecules have to have a delivery vehicle. They're very fragile by themselves. And so you have to have them encased in a vehicle. In some ways, these vehicles could either be viruses that have been inactivated so they don't cause infection in a normal way and cause problems, or we have what are called lipid nanoparticles, which are sort of a protective shield around the genetic material. And what's important about these delivery vehicles is that they have to be designed in a very specific way, such that they are recognized by the airway cell, and they bind to it tightly, and then it's taken into the cell where the genetic material can be delivered, whether it's mRNA or the gene itself. So there's a lot of work that goes into trying to figure out what the right coding of these vehicles, these delivery vehicles are, so it gets recognized in a very efficient way by our airway cells. And then finally, the delivery, and then the target cell is in the airway, obviously. And these therapies that are being developed are going to be nebulized therapies, at least the first generation of them. So you have to do they're delivered directly into the airway using a nebulizer. So this gives you a bit of a timeline of where we are in terms of the various therapies. And so on the left, you can see that mRNA therapies are in clinical trials. We actually had a clinical trial from a company called Translate Bio, a phase 1 study, which showed that the delivery was relatively safe. In other words, people were able to take the drug and did okay. A little bit of fever associated with at the highest doses, but that was the main side effect. Unfortunately, they were unable to show any clinical benefit, and so we're still working on that. The gene transfer, now this is a little older slide because we actually have a clinical trial going on now of a viral-based gene therapy. And I'll show you some information from that study that was just recently released. So this actually has progressed from a preclinical to a clinical trial. And as I mentioned earlier, the idea of gene editing is still in early discovery phase and still a ways away from any sort of clinical testing. And finally, I didn't mention this in my earlier slide, but there's an idea that you could do cell therapy where you could actually take stem cells and deliver those to the airway that have the normal CF gene. This would be, instead of delivering the gene, you actually deliver a whole cell that is capable of making a normal CFTR. Again, that's early in development and a little further away from clinical testing. So this is sort of, gives you an idea of what's being developed, which is there's a lot of work and money that's been invested in all these programs. So there are some challenges of developing these medications, these treatment. You know, it's one thing to take a pill such as Trikafta. I mean, it has its own challenges, but it's relatively easy to take a pill and get it absorbed, and then it gets into all parts of the body. These treatments, as I said, are nebulized, and so they have to be delivered directly into the airway. And as you know, most of you are aware that the CF airway is not normal. There's a lot of mucus there. It's thick. It's sticky. It has a lot of proteins. The pH is abnormal. The proteins can destroy genetic material. Excuse me. So it is a challenge to design these drugs so it can navigate all the way through this thick mucus and get into the airway cell where it actually needs to do its work. Then the other thing is that sometimes you can get an immune response to these genetic therapies. We all know about the COVID mRNA vaccines where they're designed to induce an immune response. That's how it works. But in terms of mRNA treatment, you want to minimize the immune response because you want the mRNA to be functional and produce a normal protein. And if you have to give it again, you don't want the antibodies to be destroying the mRNA. Lung cells are continually replaced, so we will need to figure out how often this needs to be given, especially for mRNA therapy. I already talked about the idea that basal stem cells are the bottom of the airway, hard to reach. And so that becomes a little bit challenging. And more of a technical issue is that CFTR is a relatively large gene. Why is that important? Well, it's because some of these vehicles that we use to deliver the genetic material to the airway has a certain carrying capacity. It can't hold a genetic a gene or an mRNA molecule that's too big, and so we have to sort of make sure that the delivery vehicle can contain the full gene, such that we have a normal protein being made, or normal enough that it'll function the way it's supposed to. And so this is a technical challenge as we design our genetic therapies. All right, so just to kind of summarize, what are the differences between CFTR modulators that we're more familiar with and some of these genetic therapies? Well, the similarities are that they both target the underlying cause. For CFTR modulator, it's a protein. For genetic therapies, we're targeting either the mRNA or DNA. Obviously, they're both novel in terms of like the idea that nothing like this has been existed before for CF. But they take a while to develop. They have long development timelines. And if you think about the first testing of modulators, probably was that back in 2006. And here we are, it took about 13 to 14 years to get Trikafta approved. So it takes a while to get these drugs from discovery to approval. So what are the differences? Well, as I alluded to already, one targets protein, the genetic therapies will be targeting mRNA or DNA. The modulators are oral. The genetic therapies are going to be nebulized. Perhaps we could develop an intravenous version of it down the road. Intravenous gene therapy is used for some other diseases such as sickle cell anemia, spinal muscular dystrophy. But for the CF therapies, we're going to be initially focused on nebulized therapies. One thing to also consider is that because it is nebulized, the correction for CFTR would be in the lungs, at least initially, compared to modulators, and where you get correction of CFTR in the whole body. So, for example, your GI tract will also respond to these modulators. Your liver would respond. That will not be the case for genetic therapies, which will be nebulized. And the other thing is that the normal clinical trials that we do for new treatments are probably not going to be applicable for the genetic therapies. And part of the reason is that there are a relatively small number of people who would be eligible for at least for the initial testing for these genetic therapies. When we have 30,000 people in the CF registry, and maybe 80–90% of those would be eligible for a modulator, the number is much smaller. We're in the realm of hundreds of patients around the country that would be potentially eligible for genetic therapy. So we're going to have to really think hard. I'll show you some information about how we're thinking about doing this testing, but the study designs are going to be different for these genetic therapies, and this is an additional challenge we'll have to overcome. So again, a little bit of a table to talk about the differences and similarities between mRNA, gene delivery, and gene editing. One thing to remember is because we're putting a normal gene or mRNA, we're delivering a normal mRNA or gene, that any person with CF would potentially be eligible, because it doesn't matter what your mutation is. We're giving you a normal gene, normal mRNA, so every patient would potentially be eligible. That's important. The dosing schedule is going to probably vary for mRNA, maybe weekly, for gene delivery, maybe monthly, and for gene editing, we don't know at this point. The delivery mode we talked about, it's probably going to be nebulized at first, at least. And the challenge we've talked about as well, that which cells will take up the genetic material and make it, and for how long. For mRNA and gene delivery, it is not a potentially permanent solution. You're going to need to do repeated dosing. For gene editing, that does offer the potential for a one-time treatment. That remains to be seen, but has the potential of doing that. So what are the programs that are currently developing or going through clinical testing? So in terms of the mRNA programs, I already mentioned Translate Bio has done mRNA. Although we didn't, we're not able to show efficacy, we did get some important safety information. So we have that available to us. The programs that are near development, or near clinical testing, are a program from Arcturus, a company called Recode, and then Vertex is also developing an mRNA-based therapy. I would say Vertex is probably the closest to starting up their clinical testing, hopefully sometime in the next couple of months. In terms of a CFTR gene delivery, 4D Molecular is the company that has actually started their phase 1 study, and I'll show you some information that they showed at the last North American CF meeting. And then 2 other companies that are nearing clinical testing are a company called Spirovant. They also have I should mention that they have an adenovirus-associated vector as a delivery vehicle, that's same as 4D Molecular. Crystal Biotech is using a slightly different approach. They have a different virus, an HSV virus that's the delivery vehicle, but they're all able to deliver CFTR gene using these different viral vectors. And so that's where we are with gene delivery in terms of the clinical programs in development. And so this is, as I mentioned, 4D has started a clinical trial, and they're obviously very early. What I'm showing you here is some safety information. And what you're seeing on the graph on the right is what happened to a person's lung function, because one of the things you do worry about is that when you give this treatment, Does it cause bronchospasm? Does your lung function go down acutely because of an adverse event? And so it was good to see that when you took this treatment, I'm showing you data from 3 people, that the lung function was stable for the first few hours after the treatment was delivered into the airway. So this is important information telling us that at least for the short term, this was a safe installation, and people did not have bronchospasm as manifesting, in a lower FEV1, as you can see on the right. Now, how do we know that the delivery of the genetic material is actually able to be made into a protein? Well, that would be sort of proof that the cells have taken up the genetic material, made mRNA, and then made the protein that you can actually see it. And so what's being done in these studies is that patients who enroll after about 4 weeks undergo a bronchoscopy. A bronchoscopy is a procedure where you're able to take a scope and put it into the, a patient will have to be sedated for this, but this is a clinically, it's a clinical procedure that's done very, very frequently by pulmonologists like myself. And so you're able to get into the lungs and get a sample, but using a brush, where you brush the lining of the airway, and you look to see if any of the mRNA, protein, mRNA, or the gene is being made. And so what I'm showing you here is data from a patient that actually underwent a bronchoscopy after getting the treatment. And all the little brown spots you see are areas where they see evidence of the gene being made into an mRNA. So this is proof of principle that you can take this medication and deliver it into the lungs of a CF person with CF, and actually see evidence of the gene being made into mRNA. And here is just a different view, again, just to orient you. Up here, you see the air. These are the cells, and this is the underneath layer of the airway. And all these brown spots here is where they're seeing mRNA being made from the gene that was delivered. And it's also important to note that they were able to show that the gene is being delivered to different types of cells, both goblet cells, ciliated cells. Goblet cells are the secretory cells that I talked about, and basal cells. So they're able to get this genetic material into different types of cells, which is obviously important. Again, showing you a different part of the lung. This is the right lower lobe. This is the left lower lobe. Again, you see these brown spots indicating that the gene is being made into the mRNA. So, this is a very early study and proof of principle, but it is the first, it's the next step to developing this for clinical utilization. So I just wanted to show this to you to show, what these studies are going to be doing, what there's going to, the information we get, what it's going to look like in terms of trying to understand whether these drugs are doing what they're supposed to be doing. And obviously we'll be looking for clinical benefit as well, using some of the other parameters we look at, like FEV1 and those kinds of things. So finally, I want to wrap up by showing you what the CF Foundation is doing with respect to trying to get these clinical studies done as efficiently as possible. As I mentioned, there's only probably a few hundred patients in the country that are going to be eligible, to have the right genotype, have the right lung function that is high enough that it's safe to do these kinds of early phase studies, be over the age of 18. We don't like to do these initial treatments in children. So, that really narrows the pool in terms of who would be eligible for these studies. And so what we are doing is we create these regional consortia, because each clinic may only have 1 or 2 people that would be eligible. And it's hard to do studies when you have so few people. So what we're doing now is we're setting up regional consortia, and in Chicago, we're part of a consortium of about 8 or 9 CF centers in Chicago and parts of Wisconsin. And the idea is that we're going to work together to refer patients to the site that is doing the clinical trial for these early phase treatments. And this is going to require a lot of cooperation and communication across CF centers and patients willing to travel to a different center in order to participate in these early phase clinical studies. This is a way, hopefully, we can optimize recruitment into these studies and try to find out if these treatments are going to work or not. So this is something was just initiated a few months ago, and it's rolling out, and hopefully this will facilitate the treatment. I'm sorry, the recruitment and completion of these early phase genetic trials. So I want to just finish by just talking about this idea that we've had incremental advances in CF. We look at modulators. And when Kalydeco was first approved, about 10% of people were eligible. Then we got Orkambi up to 50%. With Symdeko, we got up to 60%. And finally, with Trikafta, we're up to 90 or 90+% of people eligible for CF. And this took about 15 years to go from initial testing Kalydeco to Trikafta approval. So it's an incremental process, takes a while. So we're not going to have genetic therapies available this year or next year, but it's going to take a while. But there's a lot of work going on to get us to that point where we can actually get CFTR-based therapy for the remaining 10% or so people who are not eligible for modulators, and that's the goal. To have CF stand for a cure found. So those were that was the information I wanted to go through. I want to thank you for coming today and allowing me to share this information with you. And I'm happy. I think we have about 20 minutes or so for some questions. I'm happy to use that time to answer questions about genetic therapy, or if there's any other things that would be relevant, I'd be happy to answer those as well. So thank you.
Thank you, Dr. Jain. That was very informative, and I always love hearing from you in particular. You always give a great update, and it's so exciting to hear what's coming down the pipeline right now. But now we do have some time. Dr. Jain is generously giving us some more of his time. So if you have questions, please feel free to unmute yourself and chime in, or you're welcome to use the chat feature, and I'll be happy to read the questions out. But I think we covered most of the questions that were submitted during registration. But if we didn't answer your question, please chime in. George, did you have a question?
Yes, at what age are the patients eligible for the drug? The treatment that was at the top of the pyramid. I forgot exactly what you call it.
The genetic therapies?
Or Trikafta?
Yes.
Or Trikafta. I took you to ask that you were wondering what age would be eligible for genetic therapies.
Yes.
So the initial studies are going to be in people with CF who are over the age of 18. That's traditionally been done because when you're developing a new medication, we don't like to enroll kids until we know it's safe in adults.
I see. Thank you.
All right, so a question came up. So if you do qualify for Trikafta, could someone use genetic therapy treatments instead? So the short answer is yes. I don't know if you mean by a clinical trial or once it's approved. Now, the way these clinical trials are designed, most of them they are looking for people who are not on Trikafta. Once it's approved. Okay. Yes. So you could opt to begin these genetic treatments and not use Trikafta. Obviously, that would be a personalized decision based on risk benefit, the magnitude of effect, the efficacy you got with Trikafta. But if the idea is, could you do it? Yes. Some of it would also depend on how it's approved. Would it be approved for all CF, all people with CF, or would it be limited to only people not eligible for Trikafta? And that's a hard question to answer right now, but conceptually, yes.
Dr. Jain, just to follow up on that, do you think there is a drawback for people who are already on Trikafta to be added on with the genetic therapy also and then phase out Trikafta?
So you're asking, is there any downside to being on Trikafta, starting a genetic therapy, and then phasing off Trikafta?
Yes.
Yeah, it's hard for me to say because there's so much unknown about how efficacious these genetic therapies are going to be. I think theoretically, if you had something that rescued CFTR based on a genetic drug, that you got normal CFTR function, yes, I think you could then get a treatment with a genetic-based therapy and phase off Trikafta, because then you'd have normal CFTR function. But we don't know whether these genetic therapies, what percentage of CFTR activity they'll be able to recover or generate. So it's really hard to speculate. I think there's too many unknowns to really feel confident about, answering in any sort of even semi-definitive way.
What does the lung function have to be? What does the FEV1 have to be?
In terms of improvement?
No, in terms of qualification for the
qualification. So it is a little bit varied between study to study, but you have to be at least over 50%, because we feel that people whose FEV1 is under 50%, that there's not enough margin for safety to do that in those patients first. The idea would be that once you show that it's safe, then eventually it can be used in people who wouldn't matter what their lung function is if it's safe. But for the initial trials, we want to have a bigger buffer for safety before we start doing it in people who are more vulnerable.
Okay, thank you.
I think Lisa Tomasetti has a question about what happened to the mRNA trial from Translate Bio. Well, they completed their phase 1 trial, and as I said, they showed that it was safe, but they weren't able to show that the FEV1 changed in a meaningful way. And so they've halted their development program. I don't know if it's completely stopped, but we have not heard about a follow-up study from them at this point.
Dr. Jain, if I can ask you another question regarding these delivery systems, which you very nicely showed. Do you think of any other people doing any different kinds of delivery systems rather than liquid nanoparticle and the virus particle, which might be coming on the horizon?
There's different viruses. There's a program from Boehringer Ingelheim. They're looking to develop a lentivirus, which I don't want to get too much into the weeds, but it's a little bit different than the viruses that we're talking about. It's an integrating virus. But the programs that I am aware of are looking at lipid nanoparticles and viral-based delivery vehicles.
Thanks.
I think Kelly Orloff has a question about for CRMS and CFS PID, which are sort of a CFTR related disorder, patients who don't quite meet the criteria for CF. Yeah, I know. I think that potentially it could be used in people who have a CFTR related disorder, because, you know, conceptually you're still trying to rescue CFTR. Whether it'd be approved, you know, we'd have to kind of wait and see it. It's a little early. You're right to say whether it would be approved for those individuals. But just from a conceptual perspective, yes, it could be used for such patients.
See, do we have any more questions or comments? Well, Dr. Jain, I would ask if people were more interested in learning more about clinical trials, what's the best resource?
I think the best resource is to go to cff.org, or talk to your team at your CF center. If they don't know the trials that are ongoing, they can certainly point you in the right direction of how to find out. There's also clinicaltrials.gov. All these trials are listed there once they start phase 1 studies. So that's another avenue to explore if you're trying to find out. And they usually will list what centers, what sites are doing which studies. You know, one of the things about these genetic therapies is they are very intensive, and not every CF program can do them. And so it may require some travel to a nearby site to participate. And that's where this consortia idea, I think, would be very useful. Your site should know about the consortia, because this is something that's been rolled out to all CF centers.
Excellent, thank you. Well, if there are no other questions, I'd like to thank everybody for your engagement today, and thank Dr. Jain for this informative update. I think it's so exciting to see what's coming down the pipeline, and you know, stay tuned for hopefully more successful updates in the future. And
Absolutely.
And we will be hosting more town halls in the coming months, so stay tuned to the cff.org, our local Facebook page and social media, as well as our email newsletters. They always include upcoming dates. So thank you all for joining us today, and have a great weekend.
Thanks, everybody. Have a nice weekend.
Thank you.
Bye.